Now that we've defined the loss and cost functions that measure how well our model is doing compared to the training data, we need to find a way to adjust the weights and biases in the right direction so that it reduces the overall cost. And we have to do this iteratively. There isn't a closed-form solution to this problem, so we have to iterate multiple times. So if we look at these two equations here, this describes how we make those iterations. And what we have here are wk plus 1, which is the next value of the weights after an iteration. Bk plus 1 is the next value of the weights after an iteration. Wk and bk represent the current value of the weights and biases in the current iteration. So we're going to compute the next value by taking the current value and subtracting this term right here. And this term has a couple of factors. The first factor is called alpha, which is the learning rate. And the learning rate is a number. It's a hyperparameter. It's a tuning parameter that we'll use to adjust how quickly our model changes. And that number is determined empirically, and we'll look at how we do that in a second. The next term is the gradient, or the slope, of the cost function with respect to the weights. The slope, or the gradient, of the cost function with respect to the weights. And if you've had a little bit of calculus, you've seen this term before. And what that is the partial derivative, or the first derivative of the cost function. If you haven't had any calculus and you're not familiar with that, it's okay. We'll look at this intuitively so you understand how it really works. So we do the same thing for the bias. We subtract from the current value of the bias the learning rate times the derivative, or the partial derivative, of the cost function with respect to the bias. And so each of these two terms are called the gradients, all right, or the slope. You can imagine it's kind of like going downhill in that curve of the loss function that we saw earlier. All right, to explain this a little bit further and to give you some idea of how this works, let's look at a simple example that's not really related to machine learning, but it just shows you how gradients and derivatives and what this gradient descent and how it works. So what I've defined here is a simple parabola. It's y equals x squared plus x over 2. And right here I have a little bit of code that describes that parabola. I've defined a function, x squared plus x over 2, and I have a little bit of matplotlib code to plot that function. So if I plot it, this is what the curve looks like. So you can imagine if we wanted to find the minimum of this curve, and we started at some point over here, we'd want to go downhill. And how do we go downhill? Well, we go downhill by looking at the slope of where we are at any point on this curve. So if we were over here, the slope is positive, so we'd want to subtract and go down this direction. If we were over here, the slope is negative, and we want to subtract negative, which would mean we'd want to add a little bit. So let's look at how we would use gradient descent to solve this problem. And we can see the minimum is somewhere around minus 0.25. So the first thing we need to do is define the derivative, or the partial derivative, of that function. And if you've had calculus, you would know that the derivative of x squared plus x over 2 is 2x plus 0.5. If you're not familiar with calculus and you're not familiar with how to calculate derivatives, it's not super important right here. This is just, it's important to know that this is how we calculate the derivative for that equation that we saw above. Now, to find the minimum, we would use the same iteration that we saw before. We take the current value of x and subtract this term, which is the learning rate times the derivative, or the gradient at that point. And we would continue iterating this equation until it converges to some reasonable value. So I have some code down here that does exactly that. We're going to start with xk equals 0. That's our initial value. We're going to choose an initial learning rate of 0.1. I've defined the derivative function, which is this same function right up here, 2x plus 0.5. And here's my iteration, where through every iteration I'm computing the gradient, which is the derivative xk. Derivative xk calls that function. And I'm going to subtract from xk the learning rate times this gradient, or the derivative, right? And I'm going to iterate. And here I'm going to just iterate 5 times just to see how it does. And then I'm going to print out what the estimated minimum is and the derivative at that point where we got to the minimum. and I have some matplotlib code to plot out the function and the point where xk is, and also the slope. So let's run that and see what we get. So it looks like we got close to the minimum, but not exactly. We started here at 0, and we got part of the way. We're not exactly there. And if you look at the slope, it's still positive, meaning that we've got a little bit more to do, a little bit more to go. So what we could do is we could adjust one of the hyperparameters. In this case, let me just increase the number of iterations to 10. And let's see what happens. All right, it's a little bit better. We're almost there. The gradient is 0.07, so it got smaller, so we're almost at the absolute minimum, but we're not exactly there. So let me go to even a higher number, 100 iterations or 100 epochs. And there it looks like we did get to the minimum. And you notice the gradient is 0, so there's nowhere to go from there. There will be no more adjustment made to this xk because the gradient is 0. Even if we iterate any more, it's not going to change xk. So that took 100 iterations or 100 epochs to get there. So we could get there a little bit faster if we use the larger value of the learning rate. Now let's adjust the learning rate and see how it affects gradient descent. So let me increase the learning rate to 0.5. And that definitely gets us to the minimum. So if an increased learning rate gets us to the minimum, and then what I could do is I could try and reduce the number of epochs. And you see that gets us to the minimum with fewer iterations. So that means that a higher learning rate is better. So then let me try an even bigger learning rate. Let me try 1.5 and see what happens. Well, it looks like we completely overshot the minimum. We're way over here at 250. So 1.5 is way too large for learning rate. So what that means is we want the right learning rate. So a higher learning rate is better up to a point. And beyond a certain point, we're just going to completely overshoot the minimum, and the gradient descent's not going to work at all. So let me go back to a reasonable number. I think I had 0.5. And we're at the minimum. And then I can just reduce the number of iterations, and let me go just to 5 iterations. And there we get to the minimum again. So it seems like some of the best values, or some better values, for learning rate and iteration are 0.5 and 5 respectively. So you can see that these parameters or these hyperparameters we determine those empirically. And later we'll look at some other ways that we can determine those automatically. But these are kinds of parameters that we may want to tune while training our model. So a low learning rate means that it'll take longer for our model to converge, but too high of a learning rate means we'll completely overshoot and we won't get to a minimum cost. Next, we'll implement backpropagation, which is going to apply this gradient descent algorithm to adjust all of the weights and all of the biases in the right direction to improve the quality of the model.